All right, welcome back to Tollefson Physics. So what we're going to focus on today is conservation of momentum. And when I talk about conservation of momentum, I'm going to talk about the whole thing, right? I'm going to talk about, we're going to think about, is there an external force applied to the system or not? And so some definitions are such that if we look at things that only affect themselves, so say two cars crashing with no friction, nothing else going on, that is considered a closed system, and so momentum is conserved. But let's say there's friction involved. There's skidding, and so there's a force applied to my cars, and it's an external force. So now momentum is still conserved, but you have to include the impulse. Okay, so what do I mean by that? So when we are thinking about conservation of momentum, when we're dealing with a closed system and there's no external forces, you can essentially think about the initial momentum equals the final momentum. All right, we'll spell that out in a little more detail. But what if there's an external force? So if there's an external force, we need to include that. And the external force occurs over a certain period of time. And so this is known as the impulse. Sometimes it's abbreviated with the letter J. And so in a closed system, there's no external forces. So you can say the initial momentum equals the final momentum. But if you are applying a force to the system, so maybe you have an engine that's causing a car to accelerate. There's a force that's being applied over a certain amount of time that will cause that momentum to increase. Or what if you have a force that is taking away some of that momentum, say the force of friction, slowing this down, causing the momentum to go down. So this covers every single case. And so that's what you want to remember. This is not necessarily listed on your equation sheet, although something like this is listed on your equation sheet. So change in momentum is equal to force times the change in time, which is the impulse. So let's do an example. So here's an example where we're going to look at two train cars. Let's do train cars, right? So I got two train cars. One of these train cars is moving with a velocity v0. We'll just call it v0. Let's say both cars are the same mass. And then this has an initial velocity of 0. All right. So this one's moving and this one's not moving. Let's give them names just so we can talk about them. That's A, that's B. All right. So this idea, the sum of the momentum at the beginning plus if there's an external force equals the sum of the momentum at the end. All right, well, in this particular case, we're going to look at a system of the two cars. We're going to assume no friction, so there is no external force. So then this makes it a lot easier. We're going to look at what's the momentum at the beginning and what's the momentum at the end. Well, in the beginning, all I have is I have car A moving, right? So I gave it V0. I guess let's just say V0A to be really clear about it, right? V0A. So that car's moving, the other one's not. So technically, mass times 0 is 0. So I'm not going to write that out. And so this is going to equal, and these are train cars, so they're going to attach. They got little attachments here, and so they're going to stick together. So essentially, I'm going to have mass A plus mass B, and since they're stuck together, they'll travel at the same speed. I could have wrote that separately, but they're stuck together, right? So I have this total mass. Well, I actually know something about this. So the final velocity is both of them moving together. It's A and B, so I don't really need to separate those. So what's the ratio of these speeds going to end up being? Well, if this is one mass unit, and I have this initial velocity, and this is two mass units, and I have this final velocity, well, then I can see that this must be half of what my initial velocity was. right? 2 mass times half velocity gives me the 1 mass times velocity. So that should make sense that I have one thing that's moving. It's moving forward. It attaches itself to another object. It increases the mass. And since I have this increased mass, it's going to have to slow down. All right, so that is an inelastic, so I didn't say that. This is an inelastic example of two cars that are colliding. All right, the only way to learn physics is to do physics. So here's the problem from the video. Hit pause, give it a try, and then unpause it to see the answer. Here's the answer. And now that you have this, let's try one more new problem. We're going to change it so that the more massive boxcar is going to crash into the less massive boxcar. So how does that change that? So pause the video here, do the solution, and then unpause to see the solution. All right, here's the solution to the problem. This is another example of an inelastic collision where two objects stick together after they hit each other, and you can use conservation of momentum to solve.